In this special block, I would like to give some feedback on several definitions which we have introduced in week 1. These definitions were not so clear to several students, so I would like to go in more detail into these definitions and concepts. Among those definitions were the difference between the irradiance and the spectral power density, the difference between the watt peak and efficiency, the equivalent sun hours, and the capacity factor. Let's start with the irradiance and the spectral power density. So the irradiance is a unit parameter which describes power per unit area. So the unit is watt per square meters. It tells us how much energy in a certain time per area is incident on a surface. Note that this parameter doesn't have no spectral information. So if I have an irradiance of 500 watts per square meters, I don't know whether this is focused on the blue spectral part, the red, or the infrared. So irradiance only gives the power per unit area. Spectral power density has spectral information. It's the irradiance per spectral width. So if we choose a part in the blue spectrum, we have the spectral power density at a wavelength in the blue. Its unit is then watt per square meters per nanometer. So then per nanometer shows you already we selecting a spectral range. So it has spectral information. So the spectral power density shows whether the light incident on the surface contains more energy in the blue, in the visible, in the red, or infrared. And the relation between both are indicated by the integral over here. I is the irradiance, P lambda is the spectral power density. And if you integrate over the spectral power density, you will get the irradiance. As an example, let's take the AM 1.5 solar spectrum, which you also introduced in week 1, and here you see the spectral power density. Again, it's expressed in this slide in watt per square meters per nanometer. The black line over here shows you the spectral power density. So it means that the irradiance is the surface underneath the spectral power density. So if you integrate this, you get the irradiance. Another concept which I've seen some discussions and questions about on the blog was the difference between watt peak and efficiency. So I would like to explain this by taking as an example, for instance, a solar module with an area of 1.5 square meters. So such a model can have a power output of, for instance, 300 watt peaks. This means that if we put this solar module under standard test conditions, which are 100 watts per square meters at AM 1.5, the module would deliver 300 watts. So watt peak means the amount of power generated by a module or device under standard test conditions. The efficiency is the fraction of solar energy which is converted into electrical energy under standard test conditions again. So as we have discussed, the efficiency is the power coming out of a solar cell divided by the total power of light which we put into the solar cell. So if we now look again at this solar module of 1 square meters, it means that the output on the standard test condition is 300 watts. It's the 300 watt peak. The power which we put in is 1.5 square meters times the irradiance of standard test conditions, which is 1000 watts per square meter. So if we do this calculation, it means that for this example we got 300 watts over 1500 watts. It means that the efficiency of the module is 20%. There were also some discussions on equivalent sun hours. Let's consider the situation that we have a daily irradiation of 3 kilowatt hours per square meters. This means that per day we have a total energy of 3 kilowatt on sunlight which is incident on 1 square meter. We can also express this in power times time. So the power is now, if we consider again standard test conditions, thousands watts per square meters or 1 kilowatt per square meter, times 3 hours. So it means to have these daily irradiations, if we have standard test conditions, we have 3 hours of standard test conditions incident on a surface. This is equal through 3 equivalent sun hours. And this is a handy unit parameter, as if we consider again, for instance, the module of 300 watt peaks, it means that on one day, on average, if you have 3 sun hours on average, it delivers 300 watts times 3 hours is 900 watt hours or 0.9 kilowatt hour of energy. So if we would have 4 sun hours per day, it means that the average daily irradiation would be 4 kilowatt hours per square meters. There is also a relation between sun hours and the capacity factor. We also had some questions on the capacity factor. Let's look in more detail to the capacity factor of a solar module. Capacity factor is the effective time that an electric generator works on its maximum nominal power. And usually capacity factor is averaged over 1 year. So if we have 4 sun hours per day, which means that we have 360 times 4 hours of sun at 1 kilowatt per square meter irradiance per year. So it means that we have 4 hours per day that the solar cell is working on its maximum power or nominal power. So it means that we can calculate the capacity factor, and the capacity factor is then over 1 year, of course, 365 days times the 4 hours divided by the total time, which is in a year, which is 365 days times 24 hours. And then you see that for a country where we have on average 4 sun hours per day, the capacity factor is 16.7%. So the capacity factor depends on the annual irradiance of a certain country. For instance, in the Netherlands, this would be around 12 to 13%, where, as you see over here, 4 hours per day is a typical irradiation, which is in Spain. There you would have a capacity factor for PV of 16.7%. So I hope that this additional block helped you in a better understanding of the watt peak, efficiency, irradiance, spectral power density function, sun hours, and the capacity factor. I hope to see you back in week 2 and week 3 of the Solar Energy MOOC. See you!